Hello and welcome to our talk on differentiable direct volume rendering. My name is Sebastian Weiss and I will be guiding you through the steps how we make direct volume rendering differentiable. In direct volume rendering there are four main sets of parameters. The first one is the camera. Where is it located? In which direction does it point? From the camera, rays are shot through the object, and because the volume rendering integral can't be solved analytically, discrete steps along the ray have to be taken. And this gives rise to the second parameter, the step size. Once we have the sample locations, the volume density, so a 3D grid of volume densities, has to be interpolated. And this is the third parameter. From these densities, we get the color, which is then blended together via the transfer function. And the transfer function is the fourth parameter. And all those four parameters are differentiable in our method. With respect to the camera, we imagine this can be used to optimize the viewpoint, so find the best viewpoint that visualizes a specific dataset. For the step size, the change of the image based on the step size at this pixel can be used to find some way of adaptive step size. For the transfer function, we show how to reconstruct the transfer function from images. Or thinking this a step further, given a reference image from some other dataset, the style of this image can be transferred to the new object via style transfer. For densities, we show how to reconstruct the 3D density grid just from 2D images. And this can be used to also train scene representation networks from images. For the sake of time, I can go only into more details on these three applications: camera optimization, transfer function, and density reconstruction. We are not the first to attempt differentiable rendering. For mesh rendering, there's for example Lopa et al. From 2014, which present OpenDR, or Lee et al. From 2018 on edge sampling. These methods are specialized for opaque surfaces. To the best of our knowledge, the work from Nimir David et al. From 2019 on Mitsuba 2 is the first differentiable ray tracer which also interacts with transparent volumes. We will later see comparisons with Mitsuba 2. But before I can go into details on how our method is set apart from, for example, Mitsuba 2, I have to raise some theoretical background on automatic differentiation. Given here an example problem with p equals 3 parameters, a, b and c, and n equals 2 operations. f1, which takes a and b as input and produces the intermediate value d, and f2, which takes d and c as input and produces y. Now we are interested in the gradient of y with respect to a, and the chain rule gives us this. Now there are two fundamentally different ways on how to approach these gradients. The first one is the Adjoint method, also called backpropagation, and requires O of n plus p operations. Math is shown in the paper. The idea of the Adjoint method is to propagate the gradients from the end of the algorithm forward to the start, therefore backpropagation. However, to evaluate these gradients, we need to store the intermediate values from the regular computation, and this introduces an additional O of n memory requirement. And n, in the case of direct volume rendering, is very large. We have 1,000 steps along each ray and millions pixels, so a million rays. This gives rise to n being in the order of billion, and this becomes quickly the limiting factor. The second method is the so-called forward method, which requires O of n times p operations, so it's expected to be slower, but because it traces the gradients forward, together with the normal computation of the values, it requires no intermediate storage. Our method implements both of those approaches. We will later see comparisons in the timings, but our main contribution is we show how to get rid of this O of n memory dependency in the Adjoint method. This memory requirement comes from storing intermediate values, and this is actually only taking place for nonlinear functions, more specifically for the blending function. Here you can see the front-to-back blending function, and when we take the derivatives, we see they are not constant, but contain the inputs again. While we can recompute the current contribution, so C in alpha, by interpolating and re-evaluating the transfer function, the previously blended colors Ci, alpha I, usually would have to be stored. And this would imply storing billions of colors for each frame. However, the blending step actually is invertible. We can solve for the previously blended color by just recomputing the current contribution. And with this, we can evaluate the gradients with a constant memory footprint for arbitrarily many steps. Let's have a look at some results. For the camera optimization, we show the application of best viewpoint selection. So given an image loss, we use the entropy loss by Yi and Shen from 2006. What is the view that maximizes this entropy? Here you can see the initial situation, the plume is tilted to the back, and let's run the optimization. One can see that the camera shifts to a perspective where the plume is viewed up front, and this is much more optimal for the entropy. Let's have a look at the timings. Without gradients, our renderer takes 3 to 4 milliseconds to evaluate this image. The forward method requires around 9 milliseconds. The Adjoint method first has to evaluate the image without gradients and then performs the backward pass, giving rise to around 10 milliseconds. So in this case, for camera optimization, the forward method is slightly faster. Now let's continue with the second application, transfer function reconstruction. Given a dataset, here rendered without a transfer function, and some views around the object with a transfer function, what was the transfer function it was created from? We initialize the optimization with some random transfer function, and let's run the optimization. And this is here the final result. Let's compare it with the ground truth. One can see the images closely match. The transfer function still shows some slight differences, some slight ambiguities that can't be resolved just from images. We represent a transfer function as a 1D table, so 1D texture, here with 64 entries. And let's have a look at the timings and also the influence of this resolution. So here is the example with just 4 pixels. And already here, the forward method is way slower than the Adjoint method. This gets even worse with a higher resolution of the transfer function. This clearly shows that the forward method has the computational complexity of O n times p, the Adjoint method of O n plus p, and is very efficient for a large number of parameters. For even larger values, here the final result, the forward method becomes intractable. So here the Adjoint method clearly wins. Let's finish with the third application, volume density reconstruction. We look at this problem for the special case of an absorption-only method. So without a transfer function, without emission, just plain absorption. We are given a set of input images rendered from known camera positions, and let's run the optimization. Here one can see the comparison, again the reference. One can see our reconstruction closely matches the reference. It's important that we show this here for the absorption-only case, because we can use this to make comparisons with related methods. So here we make the comparisons on a slice through the object. This is the reference volume is as comparison. Because the absorption only case actually is a linear problem, meaning we can make use of the algebraic method used for tomographic reconstruction. And we use the method implemented by the Astra toolkit from 2015. And this is the result of this one. Also, we can use Mitsuba 2 as a reference, and this is the result that we obtain with optimizing through Mitsuba 2. And this would be ours. Already from just these images, one can see clear differences. Here in the difference images, one can clearly see some Mitsuba 2 underestimates the densities, so a lot of blues, and Astra introduces slight noise. So here, looking at the PSNR statistic, our method wins. When we have a look at the timings, so Astra, being a specialized method for just this absorption-only model, has the fastest runtime with 53 seconds. Mitsuba 2 is tailored for Monte Carlo path tracing and requires over 5 hours for conversions. Our method finishes in around 12 minutes. Please have a look also at the paper on how to extend the volume reconstruction for the colored case with a transfer function. And this concludes my talk. The code is available online. Thank you for your attention.